we're given vector a and b as a linear combination of the unit vectors I, j, and k, and we're asked to find 3 times vector a minus 2 times vector b. And then we'll take a look at the graph of these vectors in space and see what's happening when we find this difference. But I think it'll be helpful to rewrite these vectors in component form. So for 3 times vector a minus 2 times vector b, let's write this as 3 times vector a in component form would have an x component of positive 3, a y component of negative 4, and a z component of positive 1. And then minus 2 times vector b in component form would have an x component of 2, a y component of negative 5, and a z component of negative 3. And now for the next step, we'll perform the scalar multiplication. So we'll multiply each component here by positive 3. 3 times 3 is 9. 3 times negative 4 is negative 12. And 3 times 1 is 3. Now we'll keep this as subtraction, which means we'll perform scalar multiplication with a positive 2. So 2 times 2 is 4. 2 times negative 5 is negative 10. And 2 times negative 3 is negative 6. Later we'll talk about how we can write this subtraction problem as an addition problem. But now to find the resultant vector, we'll subtract the x, y, and z components. So the x component would be 9 minus 4. The y component would be negative 12 minus negative 10. And the z component would be 3 minus negative 6. So simplifying, we would have an x component of 5, a y component of negative 12 plus 10, that's negative 2, and a z component of 3 plus 6, or 9. But because the original vectors were given as a linear combination of the unit vectors I, j, and k, we should give the resultant vector in the same form. So this would be equal to 5 times the unit vector I minus 2 times the unit vector j plus 9 times the unit vector k. So while we do have our resultant vector, I do want to show what's happening in space when we find the difference of these scalar multiples of vectors a and b. But before we do that, it'll be helpful to recognize that 3 times vector a minus 2 times vector b could be written as a sum. This is equivalent to 3 times vector a plus negative 2 times vector b. Let's take a look at this in space. This blue vector here is vector a, and this purple vector is vector b. The resultant vector that we found is this red vector here. Let's show where this came from. If this blue vector is vector a, the vector 3 times vector a would be the vector in the same direction with 3 times the magnitude, or 3 times as long, which would look like this. So this long green vector here is 3 times vector a, and then we're going to add negative 2 times vector b. So negative 2 times vector b would be the vector in the opposite direction of this vector with twice the magnitude, which would look like this. So this gray vector here is negative 2 times vector b. So we want to find the sum of 3 times vector a plus negative 2 times vector b. One way to do this would be to take the initial point of negative 2 times vector b and place it at the terminal point of 3 times vector a. Let's go ahead and show that as well. So here is negative 2 times vector b with the initial point at the terminal point of 3 times vector a, and notice how the vector with the initial point at the origin, or the initial point of 3 times vector a, and the terminal point at the terminal point of negative 2 times vector b is our resultant vector graphed here in red. So while it is a little bit more challenging to show this in 3D, it can be shown similar to how we found the sum and difference of vectors in 2D. I hope you found this illustration helpful.